Hello, everyone. My name is Jinghui Qin. I work at SharkNet as one of the HPC technical consultants and based at Western University. My background is in computer science, focused on distributed systems and applications. The topic for today's webinar is scaling hyperparameter tuning with Dask-ML on clusters. Machine learning becomes one of the active areas these days. Machine learning applications usually involve heavy computations. Hyperparameter tuning is a common problem in machine learning. So the reason for selecting this topic for today's webinar is because of some recent user tickets that I dealt with. The users were from different universities and their research fields were different. For example, some from chemistry and chemical biology, some from statistical and actuarial science, and some from automotive and mechanical engineering, and etc. But they all worked on a machine learning project, and their jobs running on the cluster all involved heavy computations, in specific doing hyperparameter searching using the compute resources on the HPC clusters. So the common issue was how to efficiently make use of the resources on the clusters, especially when doing hyperparameter tuning in a relatively large scale. Most of those users were using the Scikit-learn package for their machine learning projects. Scikit-learn is a commonly used Python package for machine learning. It also provides a feature for parallel execution. It usually works well, especially when the search space is relatively small and the dataset fits in the memory of a single computer. Scaling up the hyperparameter tuning could be challenging because of the limited resources available on a single computer. Some problem could be memory constrained and others could be CPU constrained. DaskML extends Scikit-learn and provide a framework and tools for parallel and distributed machine learning. That makes it possible to use the compute resources across multiple computers on a cluster for hyperparameter search if needed. So this webinar, I will provide some general suggestions and some common problem to avoid when using Scikit-learn in parallel for hyperparameter searching, and also introduce DaskML for a distributed parameter search. At the end, I will give a demo on Gram cluster in using DaskML. Okay, let's get started. So let's first take a look at some general features of Scikit-learn. It is an open source Python package for machine learning, so it is accessible to everybody. And it is reusable in various contexts. It was built with NumPy, SciPy for numerical and scientific computing in data analysis, and with tools from Matplotlib for data visualization. It is commonly used for predictive data analysis. For example, it has efficient tools for building a predictive model. For handling heavy computations, Scikit-learn also has a parallel backend support through JobLib library. It particularly for working on a single machine with multiple CPU cores. That means any functions or models that are implemented with JobLib backend support, the computation workload can be processed in parallel using multiple cores available on a computer. And this is also the feature that most people used when doing hyperparameter tuning in parallel. However, it does not support a distributed computing across multiple machines or multiple nodes on a cluster if the resources on a single machine is not enough. Another thing to mention is that the Scikit-learn does not support computations on GPUs. So for today's topic, we only focus on using the CPU resources. So what is hyperparameter tuning? Here is a simple example using Scikit-learn. As Scikit-learn provides a consistent API for machine learning, if we skip the initial processing, initial pre-processing for preparing data. So the general steps are here. You're choosing model, then train the model, then you evaluate model, then you improve the model. The Python code here is a simple example in building a classification model using Scikit-learn. So the first generate some random sample data using a tool called make classification from Scikit-learn. So X here is the feature data and Y is the label data. In this example, it creates a total 10,000 samples. For the feature data X, each sample has 4 features. So X basically here is a 2-dimensional array with 4 columns and 10,000 rows. And for the label data Y here, it's a single column array or a 1-dimensional array in 10,000 lengths as n class equal to 2. So there are total 2 different labels. So the value in Y could be either 0 or 1 as the label for each sample. So next is to select a model or an estimator. In this example, a support vector classifier, SVC, is selected. It is an estimator using support vector machine algorithm, if you're familiar with that. So given labeled training data, the algorithm will output an optimal hyperplane, which consists of the support vectors that can categorize any new example for future prediction, for example. So those support vectors are learned or generated through the fitting or training process when calling this fit method on the training data. So one call SVC function here to initialize such an estimator, it involves some parameters. Here include the C, kernel, gamma, and random state. And there are more actually not listed because some default value are used. These parameters are used for different purposes. For example, the C value here is for a regularization purpose to avoid overfitting. And the kernel also has options for using a different kernel function in the support vector machine algorithm. So these parameter values are chosen before training begins. They're not calculated or learned from fitting. So these are called hyperparameters. And most models have hyperparameters. Those hyperparameters describe the architecture of a selected model. Using different values affect the fitting result. So after call the fit method to train the model, the next is to evaluate the trained model by calling this score method here. Usually it will apply on a test set for the evaluation, okay? In this example, since just for demo purpose, the data set is not split into training set and test set. So the same training set will be used here. So the model performance strongly depends on those hyperparameter values. Finding good values for those parameters is critical. Hyperparameter tuning refers to the search for good good hyperparameters. Scikit-learn provides 2 generic functions for hyperparameter tuning. One is called grid search CV, the other is called randomized search CV. So for the grid search, it basically performs an exhaustive search over specified parameter values for an estimator. a list of values are provided for each of the parameter that you want to tune. And the search is done by fitting the method on fitting the model on a data set with every possible combination of those parameter values, calculate and evaluate the score and produce the best combination. And the randomized search, the search is done similar as a grid search. The only difference is the parameter value are sampled randomly from a distribution that you provided for a particular parameter in a certain range. So back to this example here, the grid search CV is used. Before you call this grid search function to initialize such a parameter search structure, the param grid is defined with 3 different C value and 2 different kernel function to try. That's the search space for this demo example. So the total possible combination are 3 times 2, that's 6. So each of 6 combinations will be tried in fitting. When creating this grid search CV, you pass in the estimator and the param grid. Then the search starts by calling this a fit method using the grid search. Yeah. After fitting is done, the best parameter combination and the best score are produced. This is the general procedure for a hyperparameter tuning. Here, another parameter, CV equal to 5, is used. That is for cross-validation. That's also CV stands for cross-validation. CV equal to 5 means it will do a 5-fold cross-validation. If you don't specify any number for CV values, the default also is doing a 5-fold cross-validation. So I'll just list it here because I want to talk a little bit more about this. So what are the actual workload involved when calling such a grid search fit on the training data set? So to understand the actual workload involved, here are some details about the cross-validation. To evaluate different settings for an estimator, if the evaluation of each fitting was done with a same test set, then there's a risk of overfitting on the test set, right? Because the knowledge about the test set is introduced into the model and the evaluation no longer report on a generalized performance. So cross-validation is commonly used in parameter tuning to avoid overfitting on the test set. So here is a picture to demonstrate the procedure of a 5-fold cross-validation. Assuming the initial data set is split into a train set and a test set, okay. During the parameter tuning, only the training set is used. For a 5-fold cross-validation, the training set is split into 5-fold randomly, and only 4 of them will be used for the fitting, and the rest one will be used for the evaluation to calculate the score. So for each parameter combination, the fitting and the evaluation are done repeatedly 5 times for 5-fold of cross-validation, okay? So, but each time use different 4-fold for the fitting and the rest one for the evaluation. As demonstrated in this picture here, each split is for 1 round of fitting and evaluation. Then the performance score reported for each parameter combination is the average of the scores from those 5 rounds of fitting and evaluation. So after each possible parameter combination goes through such a 5-fold cross-validation, the one with the best score is produced. And then such a best combination is then used to fit on the entire training data set and evaluate on the test set for the final score or the final evaluation. So now it's clear for the demo example here, how many fittings that are actually done when you call that fit, grid search fit. So 3 times 2 is for the total number of different combination. Then times 5 for a 5-fold cross-validation on each combination. Then plus 1 for the final fitting and the evaluation once the best combination is found. So the total number of fitting here is 31 just for this small search space. Yeah, there is a way. By default, I think the final one is turned off. You can turn it on if you like to plus the final evaluation to see what the score is on the untouched test set here. Okay. So therefore, parameter tuning can be computational expensive depending on the size of the search space, the size of the dataset, and the complexity of a selected estimator. So if you want to do some quick test, you can just set the CV value with a smaller, like a 2, for example. Yeah, the default is 5. So when scaling up hyperparameter tuning, it can be challenging because of the significant workload increased, right? So some of the challenge can be memory constrained. When the data set, for example, is too large to fit in the memory of a single computer. That typically happens when a model needs to be tuned for a much larger data set after some local development. And others can be compute constrained. For example, when the computation takes too long, even with data that can fit in the memory. This typically happens when many hyperparameter needs to be tuned and the search space is large. So when considering a strategy to solve the problem, it really depends on what kind of workload and which problem you are facing. For a parallel consideration, Scikit-learn already has a nice single machine parallelism through JobLib. JobLib is a library that provides a parallel backend for Scikit-learn. It works well, particularly when the dataset fit into the memory and many cores are available on a single machine. Okay, let's take a look at how it works when using Grid Search CV in parallel. The full interface of this function, GridCV include many parameters. 2 of them are for set up the parallel execution. I highlight them in orange text here. Okay. One is called nJobs. The other is called pre-dispatch. So the nJob here is specify the number of jobs to run in parallel. Basically, it controls the number of cores used for the parallel execution. Default setting is none. That means 1, no parallel, only use a single core. You can set nJobs equal to any integer number less or equal to the total available cores on a single machine. You can also set nJobs equal to -1. That means using all of the available cores on the computer. The default parallel backend that JobLib supports for a parallel execution is to span processes, but it's also possible to manually select a threaded approach. Okay, for example, if you work on a machine with 8 cores, setting n jobs equal to -1, it will spawn 8 processes running in parallel on the 8 core. Here is something you need to be really careful about. For previous example, there are total 31 fitting tasks that will be handled by the 8 processes on the 8 core, for example. In order to avoid the delay due to the on-demand spawning of the processes, based on the documentation, the training data set has been copied for each fitting task and loaded into memory ahead of time before the fitting starts. So for the previous example, there are total 31 fitting tasks. If all of them get dispatched at the same time, it could result in a memory explosion if the size of the memory cannot hold all the dataset copies at the same time. So therefore, there is another parameter called the pre-dispatch. It is used to control the number of fitting tasks that get dispatched at a time during the parallel execution. The default setting is 2 times the n jobs. If you have 8 processes running in parallel, then 16 fitting tasks get dispatched at a time, assuming the memory can hold 16 copies of the dataset. Otherwise, you need to make an adjustment and set it with an integer number based on the memory size and the dataset size that you dealt with. Okay. On clusters, for example, if you request a full node with 32 cores on a cluster and set n jobs equal to -1, that means 32 processes will run in parallel, and by default, 64 fitting tasks get dispatched at a time. So you need to be really careful whether 64 copies of the dataset can fit into the memory of the compute node that you request. Otherwise, you will need to either change n jobs setting or the pre-dispatch setting for a proper adjustment based on the workload you dealt with. Okay. Okay, that are the things you need to be careful when considering a parallel execution. So similar situation also apply if using randomized search CV function in a parallel execution. Even though your dataset can fit fine into the memory and all available cores are fully used during the parallel execution, another problem that commonly happens is the resource oversubscription. This is also the problem that happened in some of those user tickets that I mentioned in the beginning. So oversubscription happens when too many threads are spawned. Even though you have well-controlled number of processes based on the available cores, but some nested routine or a calling math function in the fitting process has already been implemented with some library like OpenMP, which usually spawns as many threads as the number of cores on the machine to parallelize the execution of that nested routine or a function call during the fitting. Okay, and those threads and the processes are executed concurrently on the limited number of CPU cores. That sometimes could result in an overly long running time because of the significant overhead caused by the frequent context switch among those threads and processes. So that is not an efficient way of using the compute resources. And the job seems running forever in some cases, even though jobs are running in parallel. So you'll need to be careful about it. and avoid using significant more process or threads than the available number of CPU cores on a machine or the number of cores on a compute node that you requested from a cluster. So here are some suggestions. If you use joblib with the default parallel backend, the max threads that each process can span is controlled as the number of CPU cores divided by the n jobs. So that's an integer division. So when things get complicated, especially when it is not clear to you how some nested routine are implemented, you can submit a test job or run a test job in an interactive session on a compute node. Then monitor the resource usage. For example, SSH to the compute node that the job is running on, then run command top or htop to see how many processes are running. If you're using top command, you can use a dash capital H to turn on those threads spawned by each of the processes. If too many threads are spawned, you can adjust n jobs to limit the number of parallel jobs, or manually setting those environment variable to limited number of threads to be spawned in any function call. So here I listed this environment variable. You can use, for example, set them with value 1 to only to not allow any spawn too many threads, just 1 during the subroutine call. Okay. So in general, when your dataset can fit into the memory of a single node, we strongly suggest you to request a full node and do the parameter searching with the Scikit-learn in parallel, and avoid the oversubscription when running a parallel job on a single node. I also give an example how to request a full node on Gram, for example, here. If you wonder what is the memory size that a full node can provide, on cluster, here is a table with some information about the top 3 popular nodes on each of the 3 general purpose clusters. The most popular nodes on each of the clusters are highlighted in green here. Okay, for example, on Gram, most nodes have 32 core, 125 gig of memory on each. There are also some nodes with 250 gig of memory, and some with 500 gig of memory. There are larger ones as well, but less number of those kind of nodes available. So on Cedar and Beluga, the most popular nodes have either 187 gig or 186 gig on each. And the number of cores is 48 or 40, okay. You can decide which cluster to work on based on what you needed, okay. So only when the resource available on a full node is not enough. For example, you work on extremely large data set or extremely large search space, then you can consider a distributed approach with Dask-ML. Okay, here are what Dask-ML can provide. Dask provides a distributed framework to allow a job run crossing multiple nodes on a cluster. Dask-ML extends the parallelism of Scikit-learn to a cluster. It works well for medium-sized data set, but with large computations. So on clusters, pre-compiled Dask-ML package is available. So you can install it to a Python virtual environment just with the pip install -- no index. Yeah. And all dependencies such as NumPy, SciPy, Pandas, Scikit-learn, JobLib, and etc. They are included once you have a DaskML installed. DaskML also provides tools for memory constrained parameter search. For example, you're working on larger than memory data set, then you can use those Dask array or Dask data frame to partition the large data set into chunks. Then use tools like incremental search CV. But that's only limited to those estimator from Scikit-learn that support partial fit. Okay, there's a limitations here, and you need to do some more modification in your code if you consider this approach. If you're interested, you can read more. But what I'm going to introduce and demo today is to set up a Dask network on multiple nodes and connect and run a parameter search on such a distributed Dask network, assuming there's no memory constraint issue. Okay. To do parameter tuning across multiple computer nodes, it requires to set up and deploy a Dask distributed network first. A Dask distributed network consists of a centralized called Dask scheduler. It's a single, one centralized Dask scheduler and one or more Dask workers that registered with the scheduler. So this scheduler we mentioned here is a Dask scheduler. That's one process when using Dask. So to deploy such a Dask network, you need to launch one Dask scheduler process on one node first, then launch several Dask worker processes, possibly on different nodes. Dask scheduler and the Dask worker are Python executable that are included in the DaskML package. Once they're started, those processes are running like daemon processes on a Dask network. The communication among them are through MPI. So you'll need to load module MPI for Py first, then activate the Python virtual environment that you have DaskML installed. Here is an example Slurm script for launching a Dask scheduler on a compute node. Once it is running, the URL of the Dask scheduler will be written into a file with the file name that you provided. The file will be written in JSON format. Okay, this is just a file name. It's supposed to empty. You don't have this exist before you run this, okay, with this -- scheduler file option. So when starting a Dask scheduler, by default, it will also force another process to run a dashboard. On cluster, you can turn off the dashboard with this option, no dashboard. Since the InfiniBand network interface is available on the cluster, which is faster than the default Gigabit Ethernet interface for the network communication. So you can use a -- interface and then give the value IB0. That's for using the InfiniBand network. Okay, once you have a Dask scheduler started and run, you can submit a job to start a Dask worker. So here is an example of Slurm script for starting a Dask worker on the cluster. When starting a Dask worker, it needs to register with the Dask scheduler. So you need to provide the scheduler file that has the URL information of the scheduler. So the scheduler file provided here has to be exactly same that you provided when starting the Dask scheduler. Similar as the scheduler, when starting a Dask worker, it will also fork a nanny process to monitor the execution of a Dask worker. So you can turn off such a nanny process, just provide --no nanny. Okay. When a Dask worker is working, it's very often it will spill some extra data to a temporary disk. It is a good practice to use this dash at the local directory to specify the value slurm temperature to point to the local disk on the compute node for those temporary data. So to avoid any impact on the shared network file system. Okay, so you can submit multiple jobs to start multiple Dask worker on the cluster based on the resource you need. Okay, so these Dask scheduler, Dask worker not necessarily located on the same node. They could be any node on the cluster, as long as they share the same file system. Okay. After those Dask worker are launched and registered with the Dask scheduler, the Dask scheduler is aware how many workers and how many cores that each worker is running on. Once you feed a parameter tuning workload to this Dask scheduler, it will be executed using all of the cores that have been registered to the Dask scheduler by those Dask workers. Okay. After you have such a Dask network deployed, how to feed the processing workload to the Dask scheduler? There are two places. So the last slides here will provide an example how to connect to the Dask scheduler and feed a Python workload for doing the hyperparameter tuning. There are two places that you need to modify and add to your previous Scikit-learn code. So to connect and submit a workload to the Dask scheduler, you need to first create a Dask client instance by providing the scheduler file. Okay. Then you need to explicitly using Dask as the parallel backend for joblet. So here, this is the additional line you added using Dask backend. Yeah, Dask integrate with joblib to support distributed computing. Okay, then you scatter the data set for the fitting task to work on. Yeah. So not too much change, just adding this two line, but of course you need to import this library as well. Okay. You can either submit such a job to the Slurm queue or run it on a compute node through an interactive session. So here is an example script to submit such a code to the Dask scheduler. Yeah, please be aware that the parameter searching of this job will be done by those Dask workers that you have started on the Dask network, not the resource you requested in this job script. So that is why in this example, I only include a very small amount of resource request, but you need to provide enough time for the job to complete. So you have the complete output file from Slurm. Okay, that's all for the slides. Let me switch for a demo on the cluster. Okay, this is the terminal. Right now, I'm already on Gram cluster. That's on the login node. I'm in my Scratch folder. Okay, so if checking the job, I already reserved the interactive session here. I submit the interactive job on this node, Gray. So this is the interactive session. I submit, it has 8 core. I request 8 core 32 gig of memory. So here is the interactive node on this job. I will start some notebook to see, but before I do any application, I need to submit this first. You can see what's the contents of this. This I request a core 32 gig memory for this demo. So I will just do as batch to submit this. Okay. It is running, cool. Okay, we don't see any contents yet. So, because I provide the scheduler file, that will be local scheduler file. We'll see when the file is created here. It's not there yet. So yeah, takes time to start. So let's get back to here. I can start module list. Okay, module load. For Pi. I will start a notebook. Okay. Source this environment. Yeah, let's take time to launch the, let's check here to see. Okay, we have some contents output. See, you see the scheduler file is available. You can check the content. It has the URL of this scheduler. Okay. Then we can submit, oops, a desk worker. If I show you the contents. Okay, the desk worker, I request this worker with what? One of 16 core. Yeah, just for the demo. Okay. And then you start the desk worker with this, like what I showed you in slides. Okay. We can batch because this file is already available. We can just submit this. We'll see. It's running. That's very cool. Okay, we have a notebook started, but since it's running on the compute node, I need to set up a tunnel. For example, I will do this. Yeah, to do port forwarding to my local port 9999. So I can connect. Okay. Now I can use the, oops. Okay, now I connect to the notebook. I started on that interactive node. I have a notebook here to show. can increase the font a little bit large so you can see here. This is what I running before, so I can clean out this output. So yeah, I can run this cell. At the very beginning, oh, it's fast. Then yeah, see, create a client instance by passing in this scheduler. And then you see there's one worker with a 16 core. That's exactly what I requested, right? For example, if I submit another worker, oops, let's keep. We'll see, okay, it's already connected. Then let's switch back to the, if here you refresh, you see, you have 2 workers, total 32 core, and this large of memory. So yeah, it depends on what you need. You can request based on your workload. Then the rest of are the same as the example that I showed you. It creates this classification data first. Yeah, this part was just running on the local, I guess. It also possible if you didn't specify any scheduler. For example, you just create a client with empty bracket here. It will just use the local resource, not connecting to a scheduler that you deployed. So for example, it is also possible to run in this way. So if you want run this way, it only have a four worker, 8 core. So I guess a 2 for each worker. Yeah, that's the default setting. Because this interactive node, I request total 16 core, 32 gig memory. So for this way, it will just using the local resource on the compute node for the interactive job. But this one, I have 2 worker because it's a distributed Dask network. Then I define this. And when I click run this one, it will fit 5-fold for each of the 36 candidates because I have 3 hyperparameter. I'll just give some list of values for the demo. So the total fit is 180 fits. So does not include the final one. For the default, the final one, because I don't have any test set available or split. So it just doing 150 fitting on this. Yeah. Only took 32 seconds, and then you can check the best score. But if you're doing this, we can also, yeah, that's the previous example. I'm not going to run this. It took 1 minute, 12 seconds for exactly same search, but that just run locally with 16 core in total. Yeah. So yeah, I think that's all for the demo.